All right, thank you, everyone. We'll go ahead and get started. People can come trickling in. So thank you very much for attending my talk. My name is David Kjerrumgaard. That's how you pronounce that long name. I'm a developer advocate at Stream Native. We're a company behind the open source project Apache Pulsar. My talk is on real-time machine learning on the edge with Pulsar Functions. So I'm a new speaker here at NDC. I'm very honored to be here. I'm a first timer, so a lot of people don't know you. So by way of introduction, just a little bit of some bullet points about me. I'm a committer on the Apache Pulsar project, open source project, been contributing it for 4 years. Formerly a principal software engineer on Splunk's messaging team, which was responsible for running Pulsar internally for their service platform. Sorry. Audio. All right, thank you. Sorry about that. Technical difficulties. So I worked at Splunk, running Pulsar internally there. We were able to achieve over 10 petabytes a day of throughput through the system. So doing all the metrics, tracing observability of the microservices for payments so they can make sure they ensure real-time payments for one of their customers. Formerly solutions architecture director at Streamio. We got acquired by Splunk, so that's how I ended up at Splunk. And I worked in the big data space at Hortonworks before that, in the Hadoop and Hive space, working on that. So I've been at Apache for over a decade now and contributor. In my spare time, I also write books. So I've co-authored the first one, Practical Hive, about how to do, Hive is the SQL query engine that you run on top of Hadoop to do analytical queries on your data inside your data lake. I wrote the chapter on query optimization and things like that, so the queries actually ran somewhat faster. And I actually authored the entire book, Pulsar in Action. As you can see there by that free tag, it's actually available for free, so I feel like Oprah a little bit. You get a free book, you get a free book, you get a free book. If you go to that URL and download it, there's just an information paywall, so you can actually just say who you are in your email, and you get the entire electronic copy of the book, all 12 chapters, and what I cover in this talk is also covered in greater depth in that book. So feel free to, hey, I didn't understand what he was saying, go back and read the chapter, and then go on to the Manning site and say, hey, Dave, I don't understand. It was funny, some of the Uber people talked to me about that, but we'll get into that in a little bit. So I have a lot to talk. I'm very verbose, so I apologize in advance, but my topic is, again, real-time machine learning with Pulsar Functions. And the goal of this talk, this is what I want you to take away from. The goal is to give you a quick overview of the how, what, and why of deploying machine learning models using Apache Pulsar Functions. And a little quick, whistle-stop introduction of what Apache Pulsar is, because some of you may not be familiar with that. And then talk a little bit about the serverless compute framework we've written on top, called Pulsar Functions. And at the end, I'm going to give you, this is going to be a pattern, a repeatable pattern on how to say, so if a data scientist comes to you and says, I have this machine learning model, I need to put these inputs into it, and I want to run it real time, you as a developer can say, okay, I can totally do that. And I can do that in like 10 lines of code, name that tune. I can do it very quickly, so it's a very repeatable process. And hopefully, but I focus on using a fictional food delivery service to do, as the talk said, real-time delivery estimation for people who order food online, which we all did during the pandemic, right? When's my food getting here? When's my food getting here? So start with a quick whistle-stop tour of what Apache Pulsar is. So obviously it's Apache license, so fully open source, ASF 2.0, source code's out there. Go to GitHub, Apache/Pulsar, all the code's there. I'm a committer on that project. But our tagline is, we're a cloud-native messaging and event streaming platform. And so to break that down a little bit, this is the one little markety part of the speech, and I promise I'll be done with it. But we actually designed to be cloud-native up front. So other messaging systems in the past had an architectural flaw, in our opinion, on the Apache project, where they would co-locate the data with the serving itself. So they wanted to eliminate a network hop. So when you requested a message, they just go look on local disk and give you that message back. We thought that was a flaw because that becomes, on a per topic basis, if I need that data, if that node goes down, you're out of luck. That data is unavailable for some time. So what we decided to do instead was to separate those layers, and we'll talk about that in a little bit, and that makes it so we can take advantage of the cloud-native features, right? So if a pod goes down in Kubernetes, we can just spin up another one. No broker is special. No storage node is special. If one goes down, another one can take over immediately, and that allows us to leverage all the benefits of Kubernetes. We have Helm charts available, so you can deploy it yourself, and everything is there, and it's designed entirely for, again, scalability. Again, as I mentioned, 10 petabytes a day requires some elastic scalability. So hey, the load comes under pressure, we can just scale out the number of brokers. But from the 10,000-foot level, for developers like us, this is what it looks like. Very simple. Pub/sub model you're all seen for 20, 30 years now, right? You have producers. I connect and I publish data asynchronously. I don't care if the subscribers are there, consumers are there or not. They're stored in topics inside of Pulsar. And then the consumer I attach later on, and I say, I want to get data from this topic, and the data's pushed to me. That's really it. There's nothing ground shaking about that. It's the exact same paradigm, but it's, again, the architecture underneath that's slightly different. the other part of that tagline was we're both unified messaging and data streaming. So in the past, and I cover this in chapter 1 of my book, is there's messaging systems, right? And they were meant to be one-to-many. Work queue. I publish this data, you register an interest and say, I want information on this topic, and 5 or 6 people can all get it at the same time. It's sort of a work queue scenario. First one gets it, receives, that sort of thing. So they're ideal for that sort of thing. It's meant for short duration, point-to-point communications, like you're making a method call, right? Once the data's there, you can throw it away. You don't need to keep it. And so RabbitMQ and Amazon SQS are examples of these queue-based messaging systems. Then came along, LinkedIn developed this open source project called Kafka to primarily move their log data into storage. And that became the event streaming paradigm. And the big difference was that is when you're processing the log and you rewrite into another storage, the order in which those lines in the log matter, right? You can no longer have multiple consumers. They have to have one consumer getting that data and then reprocessing it. And the other thing that event streaming was designed to do is that you keep the data around longer for historical analytics. So in the messaging system world, as soon as everybody got the message that said they wanted it, you would delete it to reclaim space on that disk because disk space is at a premium. You're on a single machine, you're trying to get that back. With streaming, you intentionally keep this data around for longer periods of time, and then you point analytical tools at it, and they go back and read it, by time windowing and things like that to get that data later on. And again, as I mentioned, Kafka was what started that. Amazon Kinesis, which is just a wrapper over Kafka, is an open source or a web publicly available instance of that streaming methodology. Pulsar does both. So actually, the only system that actually does both. Getting a little bit about the architecture. So it consists of 3 different components. The Pulsar brokers there at the top, they handle all the message routing. As I mentioned, they're stateless, but with caches. So any broker can serve any topic at any time. So if one dies, another one can just take over. And that's because we store the data in a separate layer called Apache Bookkeeper. Now that is a distributed system that has replicas. So by default, you write 3 times to the data, and you can write that data there. And then how you tie that together is a metadata store. Currently is Apache Zookeeper, but we've made it entirely configurable, so you can use like etcd or something inside that's native inside of Kubernetes. And basically what you do, you publish the data to Pulsar, and then it writes it to what's called a segment, because they roll over periodically in Bookkeeper. And the metadata store is like, okay, my topic consists of segment A, and then segment B, and then segment C. And it's just a URL pointing back to where it is in Bookkeeper. So that way, so when a broker dies, another one has to come up and says, okay, I'm in charge of topic A now, where the heck's the data? It goes to the configuration store and says, oh, I can just follow these URLs and get that data and serve it. So that makes it completely, as I mentioned before, cloud native. All the brokers can die, they can come back up. You haven't lost the data, anyone can serve it. Allows for dynamic load shedding as well. One broker becomes overloaded, it can say, okay, I'm offloading these topics to this broker, and they can sort of see you have full throughput at the broker layer. You don't have any hot spotting at that layer. And that again allows us to get to those enormous scale petabytes per day. Logically, they consist of different structures, right? So obviously it's a distributed system. There's multiple instances of this. Each layer is separate and independent from themselves. We have an intelligent routing layer called proxies so that you know which topic is being served by which broker at any point in time. So your clients come in, they go through a proxy. It says, oh, you're looking for topic A. That's over here on this broker over here. And then that broker needs to get the data. It uses HTTP, and it can go read that data from the different bookies and serve those requests. So completely, again, if anyone gets full or down, you can just scale them up elastically, and so you don't have to worry about any sort of failures. Or, the runtime is up, and it can scale accordingly. But to show this better, I think a cartoon does a better job. This is a former coworker of mine at Splunk, Jack, did this, and this is kind of showing you how it happens in Kafka when you or any system that has co-located the storage with the compute. So you're in a scenario where, hey, my broker's overloaded, or my topic's full, my disk is full. I'll just add a new node, showing this boat here. Problem is, it can't do anything because it's not assigned a different topic. It can't take over the load. That broker is tied to that particular topic, and that new boat can't do anything. It can't take on new load. Where with Pulsar, you throw one in there, you can shed the load over, and that guy can immediately start taking on new load, and it just scales very easily. It's just transparent for you. So again, that's a sort of hammering home those points on that architectural difference. Last thing I wanted to mention on, because this is just a whistle-stop tour, we integrate with a lot of different things, different functions we're going to highlight on, but you can get data in and out, multiple different sources and syncs. So if you have data sitting in one InfluxDB, Kafka, whatever, you can pull it in and out. Protocol handlers, I want to highlight the MQTT because in the IoT space for real-time functions on the edge, that makes a big difference. We'll talk about that a little bit later on, why that's kind of a differentiator. We are the only messaging system that speaks different binary protocols. Before this, like RabbitMQ uses AMQP, that's it. MQTT servers like Mosquito use MQTT protocol, that's it. Kafka uses their own proprietary one. We speak them all. So if you want to have interactive systems, and when you're getting down to the IoT space and you want to have an MQTT server, you don't have to have that alongside Pulsar. You can just use Pulsar for that. And then again, we integrate with processing engines, Flink, Spark, things like that, so you can do those longer time analytic queries and things like that. So I want to give you sort of, if you want to get started with it today and using just the client APIs, I'm showing you this so that you realize it's possible, but you don't want to do it because Pulsar functions are better. So bear with me a little bit on this. But part of the Pulsar project is Pulsar Client. We have official language bindings for .NET, C#, Node.js, Java, Go, C++, and Python. There's some unofficially ones and language of your choice, Kotlin, Scala, you name it. You come to me, we probably have one that's unofficially supported. But the beauty of that we've also incorporated in our clients is that it encapsulates all that internal communication thing. So again, we're talking to a different broker, and and we get a disconnection. It automatically do a retry and reconnect for you without throwing an exception. So you don't have to worry about that in your code. You publish it to your client. It sends it out. It buffers them. It sends it out. It's going to get them back. If it fails, it's going to retry it for you automatically, and it back pressures up to your client, to your application, allowing you not to publish data. So you don't lose any data. Our guarantee is there's no data loss. If it gets in there and acknowledged, we have it somewhere in there, and that sort of thing. So it's just a sort of transparent thing you don't have to worry about. It's already built in dynamically. We use the Fluent Builder API style to sort of do these things. So you have to first create a client to create consumers and producers. This is it. This is the bare minimum. You just give it the URL of where you need to be. But in practice, you have additional things for authentication. This is my authentication token. This is my TLS certificate. Things like that get added in that Fluent Builder. But when you're done. You build it, you have it. Just showing you the Java code as well, because I'm a Java developer. So this little block of code is, okay, I want to use it. I want to start writing messages to Pulsar. This is how you do it. You create the client, as we saw on the previous slide. Then you create a producer from that client. Once the client's connected and established, now you create that client. You notice here, I want to call it that you have to specify a schema for every producer and every consumer. So we automatically, if you tell us what the type is, we enforce that when you produce it, it's going to match that schema, and we automatically take those bytes and serialize them, deserialize them for you automatically. So no matter what you do, you can sort of do these. The data is automatically transformed to the expected format before you even start manipulating it on the client side. Then all you have to do is specify, I want to read from this particular topic, and you do create. That's it. Okay, now you have a producer. Once you have that producer, you can just generate messages like this. In this case, we're again using the Fluent pattern, showing you some of the different properties. You can specify keys. We have something called a key shared subscription, so you can make sure that all the data with the same keys get consumed by the same consumer and things like that. We have additional metadata you can manipulate with, but the core is you put value there. So okay, I'm publishing a string. This is my value. You call send. This is the synchronous blocking call, so you make sure you've gotten it. We also have an asynchronous one, which returns a completable future, and you can check on the status of that and do retries, things like that automatically. But that's it. That's how you send the data. That's all it takes to do that. Summary with the consumer, you create a client again. Again, the consumer itself also has a schema. So in this case, we're consuming from the same one. You're saying, I want it to be I'm going to consume strings. I expect these to be strings. Put the topic. You also have to give what's called a subscription name. And that's a unique cursor. It tracks where you are in that topic as you consumed it. So if you get disconnected and you reconnect later on, you start exactly where you left off. You don't lose your point at any point in time. We track that cursor internally inside our storage layer. And then you call subscribe, and you're connected. And then this is just an infinite loop of I'm getting the next messages. I'm doing receive. It's a blocking call till I get the next one. And then once I get that, I process that message, you do whatever I want with it. You have to acknowledge it to say I've gotten it, and that moves the cursor forward in your subscription so that you won't process it again the next time. And that's it. It's a very simple, very, very simple framework. So if you were to do like a basic event-driven application, so I want something that says an event comes in, I process it like a work queue, here comes a work item, and I'm going to take it, and I have an inventory system, I'm going to get this data. This is that you create a producer, consumer, so you have you get the data, you process it, and you publish a result to another topic, and then you can chain it together to have multiple listeners on every one being a separate application. This is basically it. It's just a simple while loop. I got the data, I'm doing receive, I do some business logic here, and then I write out the actual result, and I finally acknowledge the message that I got it, and you move on to the next one. So that's really it. It's a very simple pattern for that. So why did I show you that? Because that's a lot of code, and we actually thought, this is a lot of boilerplate. We're going to create our own serverless event streaming framework instead that's similar to AWS Lambda or Azure Functions, something like that. It's similar in the sense that its goal, like all those other frameworks, its secondary goal is to simplify developing applications, to make it so that if you get somebody who went to CS course, one CS course, and can write a single function itself, they actually can be productive with the framework and not have to understand everything I just showed you up to this point. So you're saying, Dave, why'd you tell me that? I wanted to appreciate that's how it was. There's specifically designed to use Apache Pulsar as a message bus. So they consume from topics, write to topics. We'll see that in a minute. And the function runtime, again, as it relates to real-time processing, can be located within the Pulsar broker itself. They can run as threads. They can run as processes, and what we have specialized nodes called as function workers. And in the Kubernetes environment, we recommend it running as Kubernetes pods. So again, they can dynamically, if they die, they can be restarted automatically. They can be dynamically scaled and run in parallel. We have something called function mesh, which will automatically senses back pressure and scales up for you dynamically if that's the case. So very elastic workload processing as well. So here's sort of like I said, you can consume from more than one topics. You can have multiple input topics. Optionally, you can have an output topic if you want, and log topics. So you can capture your data and what you're processing, your logging events there. These are all the bullet points on that. Again, in the middle of that blue box is any user-supplied processing logic you want. And you can include third-party libraries. As a hint for the ML execution, that's exactly what we leverage, right? So if you want to have any sort of Java third-party library, or pandas if you're using a Python one, as I mentioned here, so there's multiple programming languages currently supported. Java, Python, and Go are supported. C# is in the future. I put a little help wanted sign there so people can help me getting the C# runtime to run properly for me. I would definitely appreciate it. It's an open source project. I would encourage that, but working on that. Customers have asked for that. They really like this feature, and they want to use it, and we're actively in the process of doing that, getting that there. But this is the basic thing. Multiple data is coming in. You execute arbitrary logic on it, and you optionally spit data out to an output topic, and this allows you to chain them or pipeline them together as well. So you can logically construct an application or microservice or ETL pipeline or whatever you sort of want as you manipulate it. You can manipulate the data as it flows through your system, as it comes through your enterprise messaging system. So this is it. This is the function A. If you can write one method and has this signature, that's it. You can have a Pulsar function. That's how simple it is. Nothing complex to process, right? So I'll leave it there for you to read for a second. It's a generic. So there's an input type of whatever you want. It goes back to those schemas that I showed you with the producer and the consumer, right? So if you want to, it's going to be a type string, and the output's going to be a type string, and that's fine. And it just has a process method. That's it. That's all you have to implement. So it takes all that code we showed you previously for the event-driven application I showed you a few slides back, these 17 lines. What all you really want to do is this do business logic. You want to take the event you have and do some logic with it, right? So why do I need all this boilerplate? And now you breaks it down to this. Now there's the process method. You're automatically, right? So every time that method is called, what happens when you submit a function is we do all that boilerplate for you. We create a connection for you. We create the client for you, the consumer or producer if you specify an output, and have that running in the background. And every time a new event comes, we invoke this method and pass in that input, the first parameter, that message, the next message. Now it's up to you. You can do whatever you want with that thing. And if you do a return method, it automatically publishes it out to the output method. So you just say return, a value. It's automatically published. You don't have to worry about any of that stuff. It happens for you transparently. Just wanted to point out that context object is also passed with you. That gives you a lot of access into what's going on under the covers, some metadata. And for our purposes, it allows us to access what's called a state store inside the bookie layer. So as I mentioned before, we have the broker layer, and then we have this Apache bookkeeper, which is a separate storage layer. It's a distributed object store. And we said, hey, we got this thing sitting around. Wouldn't it be cool if we could have our functions write data there to store it temporarily? So in between invocations, I can publish data there, or external sources can publish data there. So we'll handle any sort of raw bytes. And it has a key value map. That's it. So you publish it, you put it in there, and you can, between invocations, that data gets changed. And as we'll see, it's a backdoor that allows you to publish the machine learning models up. The data science team can just say, hey, I'll put it in the state store, and then at runtime, we do context.getState, and look for that model, boom, there it is. So it makes it very easy to get data into these functions without having to crack them open. You can dynamically change the model, as we'll see. In my use case, the models get rotated periodically, right? So it's not, once you publish it out there and your model changes, you have to tear everything down and restart it. No, you can just, this is a backdoor way in to do that. So once you have a, you've created a function. In this case, I'm using Java case, but you can, once we get the C# working, it's the same thing, but you bundle up your jar, and it has all your third-party libraries in it you want, and you deploy it, you give it the class name. This is the name that's going to be, the function name itself. And here's how you configure the input, whatever input topics you want, whatever output topics you want, and you give it a name. So you can go back and monitor it later. You can scale it up, you can scale it down, you can delete it, you can kill it. Kind of a unique identifier for that function. So that's it. Once you have it, you just publish it there, and that's it. Real simple. This, just wanted to mention, this Pulsar admin command would run on like a toolkit node or on a scikit node, but it also fronts a API, a REST API. So if you wanted to automate it in some way and do a deployment, that's entirely possible as well. It's just a wrapper around a REST API. So there's multiple ways to do the same thing. You don't have to use this CLI command, but it's just a convenient way to do it. Okay, last bit of background, I swear. So we talked about Pulsar, introductions, Pulsar functions, why they're cool, and getting you ready for that. Let's talk a little bit about edge computing environments, right? So this is, the subject of this talk is real-time machine learning. So you cannot do real-time anything processing if you have to send your data all the way up to the cloud first. There's too much latency there between the event occurs, and you do all these network hops, and you've buffered it along the way, and you finally send it to your distributed computing engine, and then they finally do something on it. Too much time has passed, right? There's this factor called a business value decreases over time, right? The longer it takes you to react to an event, the less chance it has a higher value, right? So like an IoT use case, industrial use case, you see an alert the machine's overheating. If it takes you a half hour to figure out, hey, I should shut that machine down, it probably already blew up, right? So you have to do everything on the edge. So there's some challenges with it, but there's some opportunities for use cases you're gonna wanna do. Some of them are like fraud detection, real-time fraud detection, right? You're on a mobile app and you're doing, transfer Zillow, or maybe you're on like an ATM, and you're doing something that once you commit to this transaction, you approve it, you can't sort of take it back, right? Once I've dispensed that cash, it's gone. Or if you're on like an e-commerce site, as you saw, I worked at Zappos at one time, but somebody, had ordered some shoes or something, and then later on they got the fraud detection. They said, hey, somebody charged my credit card, we haven't shipped the shoes out, so we can pull that back and we haven't lost money. But with these things, where you're doing, real-time trading or something like that, you have to detect that fraud within, a few seconds. You can't let that person sit there for a half hour, wait for their money at an ATM. You have to do it very quickly. Other use cases, we know major auto manufacturers in the United States use it for connected cars. So you have all this data collecting out on the edge. Things like, insurance companies, you plug in that little device into your thing. It measures your driving. Are you a good driver or not? It measures your rewards. They're just collecting all your telemetric data, and then eventually they send it up. But sometimes they do real-time analytics as well. Industrial IoT, as I mentioned, surveillance and cybersecurity, again, real time, it matters. You need to make these decisions quickly, and then any sort of smart city, smart farm, agriculture. If there was this presentation about the lightning talk, the guy had the robot arm and doing that sort of thing in that farm, if you saw that one, getting all that data and reacting to it in real time. So this is what edge computing is, how I define it, edge computing. It's had different terms, fog computing, edge computing. It basically means something further away, up in the cloud. You have, everybody knows what's up in the cloud, racks of servers, infinite computing, processing. And then you have something that's sort of a gateway in, and that could be a traditional server node or edge node, but you could even be further down, closer to your devices themselves. These little black bricks are the phone that we saw on the first day. These are black bricks. You're out there on a cell tower collecting information. So the data they're sending there is, like, this is my location information. This is my intent to purchase some food for our particular use case here. And you want to, the closer to the edge you can do that processing, you're actually, reducing that decision latency. You have a higher amount of time to detect fraud or, have a better computation than if you send it all the way up to the cloud. So traditionally, this is sort of the challenge, right? There's this inverse relationship. The closer you get to where the events occur, the less computing power you have to actually do machine learning, right? That's the challenge. So on the very edge, and this, again, I'm kind of skewing towards industrial IoT, but to kind of make a point. You have all these different devices, you have sensors and actuators out there, but they have no real computing power. They're there to measure temperature and broadcast it over a shortwave transformation protocol. and that's it. They just sense the environment, and maybe an actuator, if you tell it to turn something off, close a valve, it'll do it for you. But that's it. There's no computing there, so you can't do machine learning there. So the next step up is these, what they call sensor hubs. And they're basically systems on a chip. They have, hundreds of kilobytes at the most, maybe one core. And their goal in life, the whole reason they exist, is to convert these shortwave protocols, the signals they get over shortwave, like Bluetooth and Zigbee and other short-range protocols, and convert it into an MQTT protocol, which is for longer range transmission, right? And that's all they do. That's their purpose in life. Sitting further up the food chain are then what they call IoT gateways, and those are things that have the hardware profile, something like a Raspberry Pi. For those of you who have Raspberry Pi, you have a few gigs. I have the Raspberry 4, it has like 8 gigs. 2 cores now, and you can put like a terabyte of storage on it. So now you starting to get a little bit of beef on there. And then further up, you have like a traditional server desktop. And at the very top of the food chain is the cloud, right? It's immeasurable. However much compute you want, you can buy, you can theoretically get it. And so that's sort of the challenge there. Logically, they all serve different purposes, right? So again, the perception and sensor layers do that. The middle part is there just to get the data up, as I mentioned, right? I'm collecting this data. My goal is to send it up. And then maybe at the edge, you can start doing some data processing, some simple stuff, today like filtering or aggregation sort of thing. But more complex analytic processing is traditionally done in the cloud. I got to move all this data up here, right? So the event occurs, something happened, hop, buffer, hop, buffer, hop. Eventually gets up there, and how much time has elapsed while you're waiting for all this data to transmit? So our goal is to push this computing down, right? So this is where the Pulsar architecture that I talked about earlier comes in. There's 2 edge deployment enablers, things that are distinct to Pulsar that no other messaging system has in there. And the first being that it supports the MQTT protocols I mentioned, right? So you can actually speak, you can inject here, and I'll show it in the next slide, further down the chain. You can put Pulsar way down here, and it can start listening to MQTT. It speaks that language. You don't have to do another translation. You don't have to have something listening on MQTT on one side and publishing it up on the other. It can sit right there and do those sort of things. The other one is sort of a distributed compute and storage layer, as I mentioned earlier, right? So the brokers can run, as long as you have a TCP/IP connection to Apache Bookkeeper, I can publish that data. So again, I don't need to have a big hardware profile with a lot of disk. I can put it out on something like a Raspberry Pi, or even smaller, because as long as I have a TCP/IP connection back to write data, I'm good. I can run it there. And then the third part, the whole purpose of this talk is that serverless functions framework called Pulsar Functions, right? So you can actually put arbitrary code and run it down there on the broker. So when these events come in, you can actually do an event-driven architecture much closer to where the event occurred. I have this data, do something with it quickly. Don't send it up the line and wait for something to happen. Let's do it right here. And my goal of this talk is to show you how to do a machine learning one there, right? So this is sort of, the concept is you're gonna stretch it, right? So we stretch this data processing layer down all the way to the IoT gateways in theory, maybe up to the edge server, wherever you want. But we can stretch it and leave the bookies up in the data center or somewhere further up because we have this TCP/IP connection as our sort of, ace in the hole. We have that there. And so I'm allowed to push my brokers much further down and do things like machine learning that much closer to the source of the data. So let's talk a little bit about the machine learning lifecycle. And our role in it, right? So we're developers here, but the machine learning lifecycle involves not only the data scientists, it's not just for data scientists, not only for data engineers, but at the end of the day, somebody has that model and has to deploy it, and that's us, so the developers. So I'm gonna show where we fit in there and give you an overview of this particular use case, as I mentioned, is a food delivery service, and the background so you understand what's going on. But in general, it's broken down into these 5 different phases, right? There's a problem identification. What are we trying to do actually? How are we helping to help the business? What is our goal here? Then you go through data acquisition phase. You say, okay, I'm trying to solve this problem. What data sets do I have available to actually make a decision on to solve this business problem, right? And that's sort of done by the data science team, but with the help of the data engineering team. We'll get into that. Once they've looked at what data sets they have, they start the model development. This is machine learning model development, where they start building, feature engineering, model building, validation, then they do some training. And then finally, at the end of that food chain sits us, the developers, right? So they come to us, and I'll talk about what they've done to get it to us. But at the end of the day, they say, hey, I have this machine learning model. It needs these particular data inputs, and I want to run it here. And then they dump it in your lap, and you have to do something with it. And I'm going to help you do something with it once they've dumped it in your lap. So let's start with the problem identification. What are we trying to solve, right? Everybody has a phone. Everybody's used Uber Eats by now. This is it, right? So this is, again, my book walks through this, but it's a fictional food delivery company. Customer places an order. We need to give them a rough estimate of when that food's gonna get there, right? The entire time they're tracking the food, when it's gonna happen. But in order to do that, you have to predict 3 things accurately. It's broken down to when the food's gonna be ready, when the restaurant's done preparing it, how long it's gonna take the driver to finally, go over to that restaurant, pick it up, and then transit back from wherever he picked it up to wherever my address is, right? So those are 3 different things we have to do. Well, this is a hard problem, right? It cannot be solved. You can't. There's certain problems with machine learning that you can sort of pre-compute and do it offline. Like if you get these recommendations engines, if you sign up for something in email or you bought something here, they say the next day, hey, we saw you bought a lawnmower yesterday, so you might want to buy some, lawnmower blades today or something. They have that data set. They can process it in a batch, and there's a finite number of people who've done that, and they can do that data, and then they can send that, that email recommendation to you offline, what they call offline mode. But this is online mode, right? You cannot do these things. Our goal is to pair a driver with a restaurant, with a customer who pops up ad hoc, and we can't possibly pre-compute all these values. It's an NP-complete data set, and even if we could, you can't account for current conditions, right? If you possibly could, the traffic today versus yesterday, and on Friday with weather and everything else, you just can't account for that. So it has to be done online. You have to do it with real-time data. So, okay, that's our problem. Data acquisition starts by the data engineering team / data science. They sort of collaborate on this, and they say, okay, what do we have? What data sets do we have? Well, among many other things, obviously the driver has a mobile app. So he signed in, and every time he signed in, periodically in the background, we're sending a ping of where he is. This is my driver location. This is the timestamp. This is my lat. This is my long. This is where I am. And that's a big data set. We use it for a lot of different things. So you can put it in some disk-backed caches for real-time. So hey, I want to know where these drivers are right now. But then you do analytics for route optimization, and you do some pricing, right? You look at these surge pricing models and try to better place and set your drivers to be at the right place at the right time. So you forward that onto a data lake. So then you also have this more of a traditional transactional database. We still need to keep track of who bought an order, who delivered it, so we can make sure that the restaurant gets paid, the driver gets paid, the customer had a transaction credit card. We can track all that stuff like a regular business. We have all that stuff sitting more in a transactional database, and we'll just call it like a food order database, right? So it's sitting there, and it's tied back to order IDs and statuses. So the data science team and the data engineering looks at it and says, okay, intuitively, let's start calculating some things. And one of the things that, I got this from the Uber blog. This is how Uber Eats kind of does these things. They start looking at, hey, things that matter, things vary over time, right? You want to say, okay, we're trying to predict how long it takes a restaurant to make a meal. Well, that varies, right? So you don't want to calculate one average for their entire lifetime of that restaurant. You want to have it more granular, because how long does it take, during rush hour, during noon, during lunch? How long does it take at 10 o'clock at night when they're understaffed? How long does it take Monday, Wednesday, Tuesday, like this? And so you can take that data and do a query on that transactional database, something like that, and and figure it out, and then you do it per restaurant basis, right? So, okay, so this is my average time over the last hour, for example, for every restaurant. Well, that's great, but you can't do that query every time, even if you knew the restaurant ID on the edge, right? The database isn't there. It's going to take a little while to run this processing thing. So what they do at Uber and other things is they use what's called a feature store, and they pre-compute this in the background using a large processing engine, right? This data's sitting there. They make a copy of it in their data lake, and then they run this with a massively parallel processing system, and they put this in a columnar database, something like Cassandra, that has a key value lookup, right? So when I come back to look at this later, I go restaurant ID, and there's like 800 different columns there, and one of them is what was the average meal prep time in the last hour, and I can look at that information. And then you can do similar things by different day of the week. That's another different factor that they run. You can do different things about the delivery time. How long does it take for people to get into this restaurant, pick up the food in the last hour, the last week, at Monday at 4 o'clock, whatever they want, and they pre-calculate that data. So once the data scientist says, okay, this is the features I want, they make sense, I put them into my model, I've done some sampling, and it makes sense, the data engineering team goes off and sets up the framework to make sure that this is populated and runs every hour systematically. So that data is guaranteed to be there when you need it to feed your model. Right? And now us as the programmers know where the data sits, and we know the key because the key's coming in the message. We have the customer ID, we have the restaurant assigned to it. So we'll show in a little bit, we can just go get that data. So that's sort of a data prep thing. The other thing we're missing though is the distance, right? These people are popping up everywhere. How are we gonna know, how can you possibly calculate every permutation of every customer's address to where the driver's gonna be, because the driver's always moving, so how the heck do you do that? Well, long story short, Uber had to solve this problem, so they solved it for us. They made it open source. They have this thing called H3 for a spatial index thing, and what it basically does is take a map and maps it down into grid squares that are all equal distance apart, because hexagons have the property of their centroid, of any other centroid is exactly the same. And so you know the size of these things. And then you can basically say, okay, the guy's 4 hexagons away, that's 4 miles, sort of thing. And so you can just, all you do is put that driver in a hexagon. You know where the restaurant hexagon is, and you know where the customer hexagon is. And then you can simplify it because you're not solving an exact problem, you're doing an approximation instead. And so, for example, way you do, again, you do a prep. So, okay, we're gonna look up this information ahead of time. We can pre-calculate this stuff, and you sort of have an idea. What's the average time? So this centroid here is showing the restaurant. They're in the middle at that point, and you want to say, okay, what's the average time it takes me from the driver's in this hexagon to get there is 6 minutes, and you just do sort of a range because we're not going to assign anybody outside of that range, so you already have these values pre-computed. Now we've kind of solved that problem. And I say, okay, we know this guy's going to this restaurant, and the driver, every time they ping on a separate pipeline with a Pulsar function, we just embed it. We do that. We call that H3 encoder. Tag is grid square, and then we know it. We have the data. So we have the data. So last, just kind of go a little bit. So now the data science team says, okay, we're great. We got all the information, that sort of thing. Just sort of showing you what their end product's going to be at a 10,000-foot level. I'm not a data scientist. I apologize to everybody in here if I'm simplifying your job or marginalizing in any way by saying this, or anybody that watches it. But they have, basically, at the end of the day, they have 2 outputs that they're going to give to us. Here's your model. It could be of any type. It's a linear, it's a linear regression model. It's a decision tree. It's a K clusters network. Whatever they build, that's up to them. They hand it to us. And the other thing is, again, like as I mentioned, feature vector. This is the input I need. So if I have certain customer order features and delivery time features and the average meal prep features, and I put these things in there, and you give me that, and I guarantee within a 90% degree of accuracy, I can predict the time that they're going to get there, right? That's their job. That's what they do. So when they're done, what we get as developers to deploy it is going to be a model and a list of what the feature vector is. That's it. I just want to mention that there's a variety of things. So this framework, as I mentioned before, it's agnostic to what the machine learning model is or what you do. You can use data scientists on your team can use any one of these that they want. Doesn't matter. TensorFlow, they want to use pandas, they want to use R, they can use whatever the heck they want, any model type, any language toolkit they want. We're not going to have a restriction that says, oh, you can only use certain things. They toss this model over to us and the features, and it's our job to handle it. And we can handle any one of these things using this framework. Oh, did I do that? Yep. Okay, model training, this is the hard part. I'm going to trivialize it quite a bit because I don't know how to do it. I'm not a data scientist, but basically, we all know this intuitive, right? So we have the set of features, but intuitively we know that some things have a greater impact on the prediction than others, right? Like the distance probably has a better weight than the average meal prep time, or we don't know, but you sort of say they're all not weighted equally. They all can't have the same impact on the precision of that, and that's what training is. They run through this process of assigning a corresponding weight to every feature in the vector, right? So this one is 0.3, and this one's 0.8, and this one's 1.2, and that one's 0.01. And that becomes the final thing is a trained model actually has to have the weighted vector. And that's what training does, is generate a separate weight assignment for each feature in the vector. And they do that. So this is my oversimplification how they do it, but basically my understanding is they go back to historical data, they grab a random sample of training data, they push it through the model, they compare the predictions with the actual results, and then they adjust that feature and they keep either adjust, okay, this feature doesn't work, or we need another feature, or we have to add a weight to this one, or we take a weight away from this one, we adjust the weights until they get the prediction with the accuracy that they actually want, right? And that's great, and that trains a model for one particular set of data. Here's sort of the problem with that, right? Think about an international business like Uber Eats, and you're gonna train a model with one data set, and you pick that data set. Do you want to take data from New York, Los Angeles, Chicago, London, Paris, and train it on that? Because the traffic conditions are different, a lot of different environmental variables you can't account for, right? There's different things at a different time of the day. So what we really end up doing for something like complex like this is having a different suite of models. And you can differentiate them by region and or time of day, and you end up with this combination. That goes back to the state store I mentioned before. So when people need to rotate automatically a model, and I don't want to take my machine learning model offline, my Pulsar function offline, I just inject a new model, automatically rotate it in, and say, oh, here's your new model. because it's trained differently, because you can't train one model for every individual use case. That's impossible. Data scientists tell you, can't you just do it once? No, I can't. You really have to adjust for this. So this is sort of just hammering home that point that there's going to be a rotation of models. You deploy a function out on one edge, you need to use this one. Every time of the day, you need to rotate another one in the state stores. How we're going to do that. So finally, I've been talking a lot. This is our part, the developer's part. This is software development. Yay, we come in to save the day and be the champions and do that sort of thing. So data scientist team comes in and says, hey, we got this trained ML model we want you to do, right? And so that's great. We got to put all these pieces together that you handed us. So okay, what was it trained? Oh, it's a TensorFlow model. Okay, so now we know which library we need to use. We include that third-party library in the function. Oh, what's the feature vector? Oh yeah, it's this, and this. Okay, that dictates what data we need to prep. And we go back to the data engineering team and say, where am I getting this data from again? How do I get this? Oh, it's in Cassandra somewhere in this table, and I use this as the key? Great. So once we have those two pieces, it's our job to put all those pieces together. And why Pulsar functions are a good fit is because, again, as I mentioned, talked about, is the model can be stored and shared inside the Pulsar state store. We don't have to go out and look up arbitrarily. They can push it to us and change it arbitrarily on the fly, and we can get that information. We can access it directly inside our runtime. We can leverage existing ML execution engines, right? So these are, again, some Java-based ones, but if you're using Python, you can use Pandas, TensorFlow. You just pick the model you want, grab that third-party library, bundle it with your jar file. That's it, and then you can use that library just like you would any other piece of code. And the last part is the feature definition allows us we use some Pulsar functions to prep that data to do data access. So again, if it's in a Cassandra database, we just create a Pulsar function that's going to receive that first piece of information, and it's Java, so you use an existing Cassandra, Java, Python, C# library, do a lookup, publish an output topic, and here's your enriched data, and that's it. So everything there is completely doable, and this is the power of the third-party library, really. So this is the 4-step process, right? I talked about. This is the repeatable, generic, how to deploy an ML execution thing, right? So we retrieve the appropriate trained model. Makes sense. Okay, that's easy. We're getting it from the state store. Next, you initialize the appropriate execution engine, right? So the runtime, all these things you have to start up and warm up a little bit. So that's a simple call. You do it once, you start it up. Then you repeatedly, steps 3 and 4 happen over and over again as the data starts flowing in, right? 1 and 2 are sort of a initialization phase. 3 and 4 is, okay, let's actually get to work. And so again, you retrieve the data for all the features defined in the model, using a separate set of Pulsar functions, which we'll talk about in a pipeline manner, do it in parallel, and then you just pass that data in as expected, just map it in. It's a real simple mapping function, and you run the model and get the result. This is it visually, right? So again, the original message comes in, and that feature collection vector just shows that you can run multiple. You might have to get data from multiple different, feature stores or other data sources like that. You can run those in parallel. You take all that result, and it's a pre-populated feature vector, right? So it's line for line. You'd have 5 different fields. All those fields are populated, and it's in a schema that it's there. So when that event is published, then the machine learning model enable function reads that data from that topic and passes it in line by line feature vector to the execution engine, and it generates a prediction. On the back door, this is the data science team here doing its thing and being the mad scientists, and they're updating a machine learning model, and they arbitrarily decided through an automated pipeline they want to publish a new thing to the state store. We react to it, we adjust, and we have a new model, and everything starts over again. Obviously, if they change the features, they got to let us know. Then it sort of breaks things. But in general, if they're just doing some tuning of the weights, not so much. It'll just continue to work. In our case, since you're rotating in the same model with different weights for different regions and times of day, it's not an impact for that particular use case. So as I mentioned here, one of the ways you can do it, the state store stores everything is raw bytes. So you can serialize data, transport like that. In this particular use case, I decided to use PMML, which is like an XML markup thing. And you push it to the store. It can be done through a REST call automatically as part of a pipeline. So once they test it and they validate it and it approves a certain threshold, like their ML ops pipeline. Now that's what they do. They put it in there. They process the data. It achieves a prediction accuracy rate that they're okay with. They go green flag, release it to production, boom. And the part of that pipeline, they can just publish it out there. So it ties right into the ML ops pipeline. This is just showing you here if we can see it. This is showing a simplified one. So it includes the 4 fields that we needed, right? This is our feature vector, so distance, Last prep time last hour, prep time last 7 days. It tells us the function type it is. It's a linear regression model. It calculates some intermediate things, and it generates a couple different numeric predictors, right? So travel time, average prep time, average delivery time. And so you can take all that information and then you publish it out, and then how you want to act with it and show it to the user, is up to you. You can break it down line by line. You can say your meal will be ready in 5 minutes, and then keep it there, and then okay, the driver's got it, and you can adjust it, dynamically update it. But all those things are predicted, right? And as I mentioned before, it can be uploaded. This is using, again, the Pulsar admin wrapper tool. Again, this just fronts a REST API. That's it. I did not mention there's concept of tenants and namespaces, but that's where your functions, they all have to be. The takeaway is the Pulsar function you're running should be running the same tenant and namespace as you're deploying the state store. It sort of limits the scope so that not everybody can see everybody's data. Pulsar is a multi-tenant system meant to be used by multiple machines, and so, or multiple organizations within the group. And so that you just have to specify that those match where your Pulsar functions is. And then you can specify the state. You give it a key, which is just a string. In this case, you just have a predefined thing. Okay, this is my ML model. And then you put in the byte value, and it's the raw contents of the PMML. Or it can be the raw binary bytes of what you exported, a TensorFlow file, or your Pandas SS script, Pandas script, or whatever you want. Boom, just publish it up there. I've got it. It's my final product. That's it. So next, step 2. Initialize the thing. So you'll notice here, sitting inside, just to point back, this is the process method, right? This is a Pulsar function. This is one method we have to implement. We do everything here. That's it. So we're overriding it. We've created a food order ML type. That is the feature vector. That's a JSON schema that's specified, so we know what fields are going to be in there. And we're getting a food order ML, and we're just enriching. This is enrichment. The food order comes in, food order comes out. We're enriching some data. It's going to be the same thing, but with some no longer null values. But we have a blocker once. So the first thing you come in, you check if you're initialized. Our initialized check says, hey, is my execution engine up and running? Right, that's supposed to start this particular linear, this regression model evaluator. If not, go out to the state store and get me that PMML file. Okay, great, got it. This is it. This is all you got to do. Again, with the library, you just create, because you know it's a linear regression model, you say, this is it. You're going to run it, and you're going to take this, I know this model to be XML data, unmarshal it, and this is your model. Boom, feed it. And that's it. It's a one-time call. It parses the PMML for you automatically, and now you have an evaluator running inside your Pulsar function in the thread, out on the edge, wherever you want it to be. It's there, ready to go. Waiting for the next piece of data, right? Step number 3, I'm going to go back to that feature collection just to show you, okay, so the data's coming in. This, as I mentioned before, you can pipeline them, right? So we know the data coming in, this is kind of comes before the machine learning model, but in the execution of the steps, it doesn't, so don't get confused. But this actually occurs first. The original message comes in and says, hey, I want to order this food. We've assigned it to a restaurant, and so now you can go out and look up the restaurant ID, you make a concurrent call, maybe look up the distance, you make another one to do these calculations. They all run in parallel, they sync back together using like a rendezvous mechanism or something like that. You have a sort of a state store intermediate, and then you publish that feature vector out. You have all the data, all the features collected, boom, you publish it to that topic. And that's it. And you can use those functions. I'll talk about this. I've alluded to it earlier, and this is the blog I've talked about often. So this is not theory. This is how Uber does some of their optimizations as well. There, and you can reference that if anyone wants it. Please reach out to me. I'll give you that. But they rely on a feature store backed by Apache Cassandra. It's the real-time, very wide thing, and they pre-calculate these features for every individual restaurant. So when I come in, all I have to do is query. I know it's been assigned to restaurant 3, and I can get these features that have been pre-calculated automatically for me. It's a very wide. You can have hundreds of different values all pre-calculated, but the takeaway is it's a constant time lookup. I can make this call with a simple lookup call. Boom, I have all the data back I need, and I can pull back what I want. And so this is showing you how to do that, right? So I want to get the restaurant features. They're feed into my model. So message comes in. Customer made an order. I've assigned it to restaurant 1, 2, 3. Boom, I go out and I query that data. This is, again, probably not best programming practices, but just to show you, I'm just selecting, is this a query? I just pass in one value. And since I'm going to a very fast data store that's available over a TCP connection, which I have because I'm running on the IoT gateway, boom, I'm going to get this data back, and then I just populate it. Okay, just read the value out. Done. That's it. I got it. So that's because it's hard to get this data. That's why people do the processing up in the cloud, because all the data is there. So this solves the problem of, hey, I have some of the data I've collected on the edge, but I have to reach back and get some other stuff. This is how you do that, and again, it's very simple. That's it, that's the entirety of the function. So pretty easy to test, unit test, deploy, work just fine, that's it. Last step, finally. Run out of time, so I apologize I told you I'd be long-winded, so you stayed here under your own volition. But this is it, so this is it. This is back to what I talked about. So this was the initialized method we talked about earlier, right? This is the machine learning model enabled Pulsar function. Assuming we're initialized, either way, once you do the initialization, you're done. You create a feature vector. This is just a data holder that you have to pass into this particular model. The model that you got, we know is that feature vector. So we just pluck them off one by one. Okay, for our feature vector, putting it into the data source, we're just going to create this particular one, and we grab it out of our feature. And that's it. You just pass it over. So the average prep time we get from the feature vector, average prep time lasts 7 days. The driver latitude, the driver longitude, the driver grid ID, the customer grid ID. You just repeat. It's just a simple process. Whatever vectors you need out, you've pre-prepped it in the previous topic. You have all that data available, and now it's just a one-to-one mapping into the format that machine learning model needs it. That's it. You can't pass it. Hey, here's a JSON object. And go, what? It needs these certain things, but that's it. It's a simple, very, very simple, basic mapping function. Once you're done with all of that, you're wrapping up the last bit of it because I had to break it into 2 lines, but still it's a very small function. That's it. You say, okay, evaluator, which I've already initialized, evaluate this feature vector that I just populated, and return to me the travel time of that predictor thing, and then I'll update. This is my estimated time. I just, where I'm current time right now, plus the travel time you estimate, and that's it. That's all you have to do. So, in summary, I've kept you here very long. Y'all got a free book out of it, though. So, you get a book, you get a book, you get a book. Apache Pulsar can be used to create an execution environment for machine learning models on the edge. That's unique. Its architectural differences make it so that you can push all this logic down I just showed you, down as close to the events as possible. Right now, technologically, based on those resource sizes, right? It has the MQTT protocol, so it allows you to automatically, at least an IoT thing, receive those events in a native format, again, using pub/sub model. You can't do that with a streaming platform. So, and then when that arrives over that protocol, you can immediately trigger that event. So when the event comes in, boom, it gets published, run it right away. And this is a technology agnostic design pattern that you can use for anything, right? So it's, again, those 4 steps. It doesn't matter. It's really agnostics of the underlying algorithm or developed language in that way. And you just repeat this process, and you can say, hey, I can deploy this machine learning model on the edge of the Pulsar function. Again, they're great for online executions I mentioned because they're closer to the edge. You can dynamically swap out the trained models, as I mentioned, which is kind of a big deal. You don't think about, hey, I've got one. Okay, what about when I need to change it? Well, not so much. But here, it's very easy with that state store. It's a backdoor in, and you just look up that data or any other data. And then again, you could leverage in existing execution engines, frameworks, third-party libraries for client lookups, for retrieving the data from the feature vectors or from the feature store for your feature vectors, or for execution of your machine learning models. And you don't impose any limitation on the data science team. Hey, we can only run models of this type. No, we can run anything you throw at us. Just give it to us, and we'll do it here. So with that, I'll stop talking, other than say thank you for attending very much. Here's our QR code if you want to scan it to get more information about Apache Pulsar, about Stream Native, about us. As I promised, the code is available. That's my GitHub repo. It is it's based on the book. So it's a 12-chapter book. I have microservices based on everything from order entry. The last couple of chapters are focused on this very topic about machine learning, chapter 11 specifically. All that code is there. Play with it. I'll comment on it. Tell me how good it is, how bad it is on that. Just want to mention, if you want to learn more about Apache Pulsar, we have online training. You have some sessions, and I was actually fortunate enough we have a framework that allows you to, as part of the training, you can spin up an own VS Code interactive shell, and you have a Pulsar cluster running there right beside you, and you can just use C# and run through the code and play with it all you want. And it's there to use, and it stays up for 3 days, and it goes away, but you get a new one. So, hey, I want to try Pulsar, but I don't know Kubernetes. I don't know Helm. I don't want to spin up a whole big thing. Just go there and start playing with it. But also Docker. We have a standalone Docker image as well. But don't let that be a barrier. If you want to go there, it's all free. Do some training. Highly recommend if you're interested in learning that. If you want to come work on this cool stuff, all kinds of jobs, like everybody. We're hiring like everybody else. And puzzle pieces, last piece of the puzzle you're missing. I'll answer any questions you have. Thank you again for your time.